Okay, let's get it started. We don't have many people here, but I cannot blame them with this weather. So let's get it started. Maybe more will join us. But anyway, today we are going to continue with a bit like similar things as what we learned last week. And very important GIS stuff. So we will start with doing overlay analysis. All of you are familiar with GIS, and you know that very often you have to do some kind of overlay analysis between different vector data sets to see what are the common areas between different polygons, for instance, and how you can read the attributes from, for example, one geometry to another one. So that's the first thing we will be doing today. Then we will continue with aggregating geometries, another useful thing in the world of GIS. So we will see how we can aggregate geometries into bigger units, for example. And then we will have one small part which is about simplifying geometries. So if you have a shape of if you have a polyline that is very complex and you do not need that level of complexity in your geometry, then we will see how you can quickly make it a bit more simple if that's what you need. And then we have another important part to today's lesson, and it will be a big part of also your exercise this week, and that's data classification. And that's another thing that we do quite a lot in data sciences in general, and particularly in GIS we use that quite a lot. We are going to revisit the topic of classification on the last week when we work with raster files, so there is also relevant to do reclassification. So the library that we get to learn about today, we will revisit on the last week. Yeah, so that's those are the topics we will be covering today. I started the recording. Yeah, so let's get it started. If you haven't pulled the latest changes to the lesson materials, please do it right now. Then you should have a new folder named Lesson 4 with 4 notebook files covering each of the topics I just introduced briefly. So let's start with overlay analysis. So overlay analysis are GIS operations in which 2 or more vector layers are combined to produce new geometries. So you do this based on a certain kind of operation, and these operations are a bit similar to what we did last week when we were working with the spatial queries. So the logic is a bit similar. So there are a number of them that you can choose from, and they are provided by Shapely library. Again, another library we have seen many times during this course, but when we are working with GeoPandas, you can just access this overlay analysis through GeoPandas. But anyway, it comes with Shapely. So we have intersections. So if you have 2 polygons, in this case, one of them square, one circle in this example, and if you want to do intersection, then what you get as the output is the area that is common between the 2 polygons. If you do union, then you will get a union of the 2 geometries that you have. Then we have symmetrical, then we have difference. So depending on, if the square is called A and the circle is called B, this is the output of A minus B. So if you do B minus A or the circle minus A, then this part would have been green. But this is difference, and then we have symmetrical difference, which you can guess. So it's the union of the 2 side differences. So A minus B or B minus A. So it's the union of them. So it's all the areas except the intersection. So these are the most common types of operations that we use in overlay analysis. There is another type that we will see later on. But yeah, so that's what we have. So we want to do overlay analysis. We are going to work with a data set that you will see quite many times during this course. And that's I don't remember if we saw it already, but we will see this still a few more times during this course, and that's the travel time matrix data, which is actually produced in our own department. So it's made by Tuuli Toivonen team, DGL. So it's a very common data. They use it a lot in the cities. in the Helsinki metropolitan area and also in research. So it's basically a very big grid network. And this is a data set that this will be one of the options for your final assignment during this course. So it is a very large data set consisting of thousands of CSV files or geopackages if you prefer. And it has basically all the travel times and distances from any grid in Helsinki metropolitan area too. So you can imagine if there are thousands of grids covering the Helsinki area, what are the combinations? So it's a very huge data set, but very useful one if you're working with accessibility related topics. So this is the data we will be working with, but only one of those CSV, or in this case, geopackages, so just one file. And that contains the travel times from all Helsinki metropolitan area to Helsinki Central Railway Station. So it's just one of those CSVs. So we will work with this data set. Another vector data we have in this case is Helsinki municipality borderline. So what we want to do today is to use this overlay analysis to do something similar to what we did last week. So last week we used a spatial join to clip our data based on a certain extent. So we are doing a similar thing today. So we want to keep only the grids that are within Helsinki area, because the grids, the data comes from the whole Helsinki metropolitan area, covering also Espoo and Vantaa. So we want to just keep Helsinki. So now we will use overlay analysis, and we will do an intersection to only keep the areas that intersect with Helsinki border. So that's the agenda for this part of the lesson. The data is already there in the data directory. We start by running the first cell to load the data, to define the path first. In the second cell, we are reading the data. So the first data set, which I already mentioned, is the grid data, which is in geopackage format. And then we are loading the Helsinki border, the municipality border. So let's just run this cell. So now the data should be loaded. So before we start doing anything, let's just quickly plot our data to see what we have and what we are trying to do here. Because we have two layers, the grid and the border, I'm going to create an Ax object. So Ax equals grid.plot. So I will just add my grid first. You can choose what face color you want. I'm going to make it just gray. So the second thing I am going to add here is the Helsinki border. So the output is actually already there because I forgot to clear the output, but let's just write it again. So Helsinki.plot, and then we are going to add it to the Ax object that we already created, and then you can choose what color you want. I want to apply none as the face color because I just want to keep the outline of the polygon. So this is one way of just keeping the outline and getting rid of the infill of the polygon. And then you can choose what edge color you want to apply. So this is the color of the outline of the Helsinki polygon. And I'm going to apply blue, but you feel free to try different colors. And again, like I said last week, next week, we are going to cover visualization a bit more, so we will get into details of this. But for now, this is enough to just create a quick plot. So this is the output. These are grids because it's so dense. You don't see the grids actually, but these are grid cells. And then this is the Helsinki area. So what we want to do is to perform a map overlay intersecting this polygon area with these grid cells and keep only this area that falls within the border of Helsinki. Yeah, so as I said, this data is quite big. So from Helsinki metropolitan area, it actually consists of 13,000 grid cells. So it's quite big. So one thing that I mentioned last week, and I'm going to again say today and highlight it, is the coordinate system. Whenever you're working with anything overlay related and you're comparing different data sets, it's important to make sure they're in the same coordinate system. You might have become a bit lazy with some software like ArcGIS that take care of things a bit. But when you are working in Python, no one is going to do that for you. So make sure that they are in the same coordinate system. Before I continue, I would like to see what coordinate system my Helsinki border comes in. So I will print helsinki.crs to see what is the coordinate system of my Helsinki data. So it comes in 3067. For those of you who work in Finland, you're familiar with this coordinate system. It's this transverse Mercator data that coordinate system that most data sets in Finland come in. So that looks good for our purpose, but let's make sure that the grid is also in the same coordinate system. The code is typed in. We just have an assertion here to make sure they match. There is no error, which means the coordinate systems are the same in the two data sets, which is great. So we don't need to project our data. So now we can do the intersect. So as I said, we already saw 4 types of map overlay. We had that image at the beginning. So we had the intersection, we had union, symmetric difference, and difference. Identity wasn't in that image because it's not very graphical. So what identity is that when you use identity as the type of operation, it keeps the geometry. So it keeps the areas of the first geodata frame, and we will see how we do this. So it keeps the geometry of the first part. So if you do geodata frame A overlay with geodata frame B, it keeps the areas of A. And in cases where there is an overlap with the B, it reads the attributes of the B data into A. So the output will be the A. Wherever there is an overlap with B, you get the attributes to your data. So where is this useful? For example, I have a data set of people's home locations in Helsinki area. I've gotten it from a survey or from, I don't know, statistics, some statistical data. And I want to know wherever I have data available, I want to know what is the population around their home, similar to what we did last week. So if you do an intersection, wherever there is no population data available, you will lose your points because there is no intersection between the population data and the points. But if you use identity, then you can keep all the points, but wherever there is a matching population data, you will read that information to your data, right? So that's where we use identity. It's a bit less, that depends on what you do, but you might have seen it a bit less often than the rest. Yeah, so now what we want to do is intersection using map overlay. So I'm going to create a new geodata frame and call it intersection. So it will be the output of my map overlay analysis. And this is how you do the map overlay. So first you put the name of the first geodata frame that you want to do the overlay based on. So then we have to put overlay. So it's a method coming with geodata frames. And then you provide the name of the second geodata frame that you want to, the second part of the overlay. And what you need to specify is the operation. So those options that I mentioned. So do you want to do intersection, union, difference, symmetric difference, or identity? So in our case, it makes sense to do intersection. So I will just provide that as the value for our how parameter. So doing map overlay in GeoPandas is as simple as this. So let's just run this. Now that we ran this, it was very quick. Now let's just quickly make a plot to see what our output looks like. So I use intersection.plot. And as color, I'm going to apply blue. So yeah, so we did the intersection, and we have what we are seeing as the output is actually this area. So whatever, all the grids that fall within this boundary came out as the result of the intersection. So this is one easy way of doing this kind of clipping. What we usually do this like using a clip tool in ArcGIS or QGIS. But this is one way of doing that in Python, just using map overlay, and then you choose intersection as the how parameter, as the operation type. So let's also take a look at our data. So I'm just going to look at the head of the data using intersection dot head. Yeah, so we have, this is the structure of this grid data that we have. So we can see that we have the, well, we have all the columns there. Only the rows corresponding with the grids that fall out of the boundary are excluded here. So these are the columns. We are going to use this later on, but and there is a link here to the source of data. It's open data. You can just use it if you need it at some point. But different columns mean different things. Yeah.
I have a question of the intersection is the original grid, like the grid, and it looks like it's kind of flipped almost. It looks like the northern boundaries moved and not the squares. And then like what happened to the attributes of the like squares along the northern border of Austin? That makes sense. If you look back at the shape.
Yeah, the attributes, or you mean the shape?
Well,
the geometry.
I assume it's like cutting through the square along.
Yeah, I guess it keeps them as full. So as long as it intersects, it's a bit like similar to what we did last week. So it's doing an intersection. So if it is touching the polygon, the intersection is true. So it keeps that. So it's not really clipping, but as long as the output of intersection is valid, is true, it's going to keep it. So it's not really clipping like the geometry. It's just you're doing an intersection. Yeah, so it doesn't touch the geometry of those. They will be whole grids. Yeah, but good question. Yeah, so it's not clip. Don't confuse it in that way, but a way of spatially filtering your data. Yeah, so these different columns correspond with different values, so there are different things. So we have from ID to ID, so the calculations are from what place to what place. I don't remember everything, like what each column means, but this is like car travel distance during like middle of day, at rush hours, at different times. And I guess this car RT that we will use later is like travel time by car during rush hours. Then we have public transport, midday, late night. So different columns calculating different travel times and distances using different modes. Yeah, so that's one thing. The other thing is that when you're doing an intersection, so it's not only good for clipping or spatially filtering your data. Another thing that happens here is that when you're doing intersection, you're doing overlay, you read the attributes also from the other one. So not only you kept the geometry based on that intersection, but wherever there was intersection, you got the values from the other one. So up to here, walking time is coming from our grid data. So these are the travel time information, but all these other things like name in Finnish or name in Swedish or different code and stuff like this geometry, it's coming from the second one. So it's coming from the boundary of Helsinki. So when you do the intersection, you get the attributes of the other one into the first one. So yeah, so you have all the columns from the first geodata frame plus the columns from the second geodata frame. So now we have it as a geodata frame. If you want to save it, then, well, let's just save it because we are going to continue working with this in the rest of the lesson today. So I'm going to save it as a geo package and add a layer called travel time matrix Helsinki region. So let's just run this. This saves the data into our data directory. So one thing that you have seen but we haven't really talked about a lot is geopackages. So we have been already using them, reading data from geopackages, saving data from geopackages. And last week I mentioned that geopackage is more like a geodatabase if you're comfortable with ArcGIS, for example. So it's not just a shapefile, it's not just a single file. So it's a place where you can keep multiple layers, and not all layers need to be even vector. So you can have raster and vector at the same time. So just a quick information box here showing that you can, well, just what we did. So when you're saving a file to GeoPackage, optionally, it's advised, but it's optional. You can also provide a name of layer. So you can save it to example.geopackage, and you can provide a layer name, exactly like what we did here. And it's a good habit to do that, but you don't have to. If you know that you only have one file that you want to save in that GeoPackage, then you don't need to have a layer. But it's a good habit to do that. And then when you're reading your file, well, as I said in the first, I guess it was in the first week, these reading, writing capabilities of GeoPandas are coming from another library called Fiona. So using Fiona, you can list the layers. So if you have gotten your GeoPackage from somewhere and you're not sure what layers are included in the data, so using Fiona.list layers and then putting the path of your GeoPackage, you can get a list of all the layers that you have in your GeoPackage. And then if you are interested in reading a certain layer from your GeoPackage, you can just use the good old GeoPackage geodata-frame.read file, geopandas.read file, the name of the file or the path to the file, and provide the name of the layer. So this was just a quick note how you can work with these layers. And these layers can be raster, you will see on week 7, or they can be vector. Yeah, so if you don't have any questions, we can move on to the second part of our lesson today, which is data aggregation. So it's this notebook called Vector Data Aggregating. So do you already have any idea what is data aggregation? I'm sure you do have some idea, but so data aggregation based, and it's not limited to GIS. In GIS, we have a geographical component added there, but in working with any data. So when you aggregate data, it means that you have them in a smaller unit. You just move them to a bigger unit. So, for example, let's go with a geographical example. You have data, population data, different socioeconomic data from all countries in a continent, let's say in Europe. So you know a population of Finland, you know a population of Sweden, Germany, and many other countries. But you are interested, and you have this for all the world. So you have on a country level information about population and different socioeconomic characteristics. But what you're interested in, like whoever has employed you for a job, hired you for a job, is interested to have those values on a continent level. So they want to know what's the population of Europe, not Finland specifically. So what you do, you will aggregate your data in a bigger spatial unit. So you have all the information from all the countries in Europe, you aggregate them in a bigger unit, which is the continent, Europe. So that's aggregation. So very often, you might do it for many reasons. One of the reasons is that, okay, you need the information on that aggregated level. You want the information on continent level in this example. Sometimes it's for geoprivacy. So if you want to anonymize data, that's one way. So example, you have living location of individuals as points. So if you want to publish this data somewhere, it's problematic. You cannot publish people's home locations. So one thing you might want to do is to aggregate it to a bigger level. So instead of saying that this person lives exactly here, you can say this person lives in cupola area. So you're aggregating your data from a point level to a larger spatial unit. So this applies, this is a geographical example. You might do it for any variable. You have age, exact age of individuals. For protecting their privacy or for whatever reason, you might aggregate it to bigger groups. So you can have 10 to 20, 20 to 30, 30 to 40 age ranges. So that's the idea of aggregation. And that's something we are going to do now. So in GIS software, this is like called with different names. And but the broad term, the general term for this concept is data aggregation. So what we are going to do in this part of our lesson is to continue working with that grid data that we have. So we will work with this intersection geo package. So it's the grid data that we clipped or we got after the overlay. So it's the area, the grid data only from the Helsinki area, so not the Helsinki metropolitan area. So we are going to continue working with that. In that data, we already took a quick look at the columns in that data set. There is one column called car underscore R underscore T, and that's the car travel times to from old Helsinki area to central railway station of Helsinki. So this is the column that we have, and we want to do an aggregation based on that. So aggregate all areas, all those grids that have equal travel time in minutes to the Helsinki region. So you can imagine there will be probably a radius of places around city that have similar travel time to Helsinki. So that's the idea of this part of lesson, to do an aggregation based on the car travel time to Helsinki railway station. So is this clear? Do you understand what we are trying to do here? Yeah. So very often, well, always, when you're doing data aggregation, you have to do your aggregation based on something. So let's get back to the example of population per country, and you want to aggregate it to continent level. So if you want to do this in GIS or whatever software that you're using, whatever environment you're using, you need to have a column in your data telling which continent that country belongs to. Based on, otherwise you have to do this manually, which doesn't make sense. So if you have a data, name of country is one column probably, then there has to be a name of continent, so Europe or Americas or Africa. Then based on that column, you can aggregate them. So whenever two countries are from the same continent, they have a shared value for that column, they fall into the same category, same aggregated category. So you always need that. So in this example, we are using this column, which is travel times in minutes, as the column that we will use for our aggregation. So let's get it started, and we will see what we are doing, then it makes more sense. So we run the first cell as usual, defining the path. Then I'm going to load the data we just created in the first part of our lesson. Okay, so now that the data is loaded, we can start by doing the aggregation. And for aggregation, there is a method called dissolve in GeoPandas that we can just access easily. So I'm going to name the output as dissolved. And then I'm going to use intersection, which is the data I just loaded. From intersection, which is a geodata frame, I can access this dissolve method, which is a function that does this for me, this data aggregation. So what this function needs, like there are a number of parameters you can pass in. You will see them later. But one thing that you have to provide is the name of the column that you do the aggregation based on. So remember, with the countries, this is the name of the continents. So in this case, we are doing the aggregation based on the travel time by car. And this was the name of the column that we are going to use. So car underscore R underscore T. So with dissolve, with this dissolving method or function, you have to provide at least the name of the column based on which you will do the data aggregation. So that's how you perform data aggregation in GeoPandas. to see what we get as the output, let's also print the head of our output. So dissolve.head. So you can see that it's very quick. And this is the output. We are going to continue like evaluating what we are doing here. But before we continue further exploring our data frame, let's run this cell, which just prints the number of rows we had in the original data before dissolving and after dissolving. Let's see how the numbers change. So in the original data, the one we had after doing the intersection, we had 3,826 rows of data. Once we did the aggregation, we ended up with 51 rows of data. So we had 51 unique values, like in terms of minutes, travel time by car to Central Railway Station. That's why when you do the aggregation, you end up with 51 units. So these were the unique values we had in our data. So the data is aggregated, is much smaller in terms of like number of rows you have. So let's also take a look at the columns that we have in our data to see if anything has changed there. So from dissolves, I'm accessing the columns. So do you notice anything different here compared to the original data we started with? There is one column missing, and that is the column that we used as the column for our aggregation. So when you aggregate your data using a certain column, that column kind of disappears for your geodata frame, but it doesn't really disappear. It becomes the index of the output. So if you just, I don't know if you paid attention, but when we got this data head from up here, so you can see that the car underscore R underscore T became the index of the output. So whatever column you use for your aggregation becomes the index of the output, and it makes sense. It works well because it's unique, because it does the aggregation to unique values. Then it works as an index. And it is handy because you can just easily access a certain row in your data using a value. So now we know the index is travel time by car to Helsinki railway station. So if I want to just see which areas have 15-minute travel time to that place, then it's just the index. I can just look for that index. So let's see how that works. But before we do that, let's just confirm that it has become the index of my data. So from dissolved, I will get the index. So you see that I was right. So the column that we used for aggregation, car RT, became the index of the output data or output geodata frame. So like I said, this can be nice depending on what you need. For example, if I want to get all the areas that are 15-minute car, like driving time away from Helsinki railway station, I can just use log. So from dissolved, I can just use log and get areas which are 15 minutes away. So you can try it for different values as long as they exist. So this gives me some information. And the output has become a multi-polygon because there were multiple polygons. You aggregated into one. So there are multiple polygons which used to be separate as like polygons, but they're under one row now. So they became a multi-polygon, something that we saw in the first week when we were working with shapely geometry. So that's why we have a multi-polygon suddenly now. But let's check the type of the output we have. So type dissolved. So I want to specifically see what I get when I do this dissolved dot log 15. So this is just one row in my data. So it makes sense that the output is a pandas series. So it's just one row. So if I want to, for example, visualize this now, it's a bit tricky now. Well, we will see how we can do it. But it's a pandas series now, so you cannot just use dot plot. You have to do something before. We should make it a geodata frame first. But yeah, so it's just, you're using log to get just one row of your data, which is a series, not a geodata frame anymore. So now we want to visualize these 15-minute grid cells. And as I said, it's a series, so you cannot just visualize it like that. We have to make it a geodata frame. So I'm going to name the output geodata frame selection. And we already have practiced this, so this is how you can convert something to a geodata frame. So from GeoPandas, I access the geodata frame. And what I'm trying to convert to a geodata frame is that one row in my data. So it was called dissolved, and I was accessing using log the row that was corresponding with 15-minute travel time to railway station. So another thing you need to provide for this to work is the coordinate system of your geodata frame, and we didn't change anything in terms of coordinate system, so it's the same as the original. So I'm just going to use the coordinate system of dissolve.crs instead of typing it again. So now the selection is, so we converted that one series to a geodata frame, and it already had a geometry column, so that wasn't the problem. We just specified the coordinate system. So now that it's a geodata frame, it's easy to visualize it. So let's just create an X object because we want to add 2 layers. First, I will add the dissolved layer. And I'm going to apply a gray face color to it. The second thing I'm adding to this is the selection, so what we just converted into a geodata frame. So selection.plot. I will add it to the same X object we created. You can choose what face color you want. I'm going to use red this time. And this is what you have as the output. So these are all the grid cells that from which you can drive to Central Railway Station within 15 minutes. Like not within, but exactly in 15 minutes. So this was one way of doing that, and the reason why we did this was that because we wanted to visualize this based on the travel time, but the problem was that the travel time was no longer in our geodata frame, it had become the index. So in order to access it, we had to use the log method from pandas. So one other way, depending on what you want to do, how you want to do things, there's another way of releasing that column from index, and that's by resetting the index. So this is another way how we can visualize this. So let's do this differently now. So I will create the dissolved again, or like just overwrite it. And I will just use dissolve.reset index. And let's just look at the output using .head. So what this does, it just resets your index. It creates an index which is an integer starting from 0. And as a result, your car RT column is now released. So it's free now. It's not indexed anymore, so you can just use the good old methods we knew already to plot that particular column. So let's see how we can do that. So I will create another plot based on my dissolved geodata frame. And when you're plotting or creating a map, you can provide the name of the column that you want to use for the visualization. So in this case, now that we have released this car RT column, so I can just use it for my visualization. And this gives you the output. So now you have a visualization of the travel times based on that one column. Later today, we will see how we can modify this visualization a bit using different color schemes and also classification. But also, again, as I said, we will revisit the topic of visualization later on. But for now, this looks good. So, okay, so one thing we didn't talk about, but it's actually a very important part of data aggregation or any kind of aggregation, is that, okay, when you dissolve, when you aggregate, now we know what happens to the geometry. So if you dissolve countries of Europe into the bigger unit of Europe, so what is the output is the boundary of Europe or the union of all those smaller countries. So that's what happens to the geometry when you do aggregation. But what happens to the other columns in your data? So if you had population of different countries, if you had a column called population in all countries, when you do the aggregation, what happens? Because you only end up with one population in the output. So what country's population is that? So that's one of the reasons why we might do aggregation. So you want to get the statistics. So you might be interested in the sum of the population. So if they have told you what is the total population of Europe, then what you want to have as the output is the sum of all the countries that are aggregated to each other. Or you might be interested in the average population per country in Europe, which doesn't make sense, but that might be something you need. So then you might get the average. So when you are doing the aggregation, so I have added an information box here with this. So when you're doing the aggregation, by default, it just uses first as the type of aggregation for other columns. So for your columns, it's the union for the geometry. So it's the union of everything you have. But for other columns, you have population, you have travel times in our example. You have to choose how you aggregate them. By default, it's first. So it just picks the first value that appears there, and it gives it as the output. So it's a bit arbitrary. But it works for everything, because if you put average and you have text, but it depends on what kind of data you have. With numbers, average works, sums work. With first, then it can be anything, number or text, it works. But of course, depending on what you want to do, you can specify how you want to aggregate the columns. And this is how you can do that. So this is what we did already. So we said aggregate, let's dissolve the intersection geodata frame based on car, RT column. One optional parameter you can provide to this function or method is the aggfunc. So it's the aggregation function. And there are a number of values you can choose from. So you can use sum. So these are statistics. Sum, mean, minimum, maximum, first, and last. So as I said, by default, we didn't say anything when we did our aggregation. We got the first. You can say mean. Then it would have given you the average travel times, or maximum travel times, or the sum of them. So this is something that you can provide depending on what you need to do. And so there are times that you want to treat your different columns differently. For example, as I said, you are interested in the sum of the populations, but you might have a column that has text in it. So then sum doesn't work. You will just get an error that it cannot sum up strings. So in that case, you might well just want to use something else. You want to use the first value or the last value. So if you want to treat different columns differently, you can do it this way. So when you do the dissolve, then you can group them by and then apply an aggregation. And then you provide a dictionary saying for each of the columns you want to use a different aggregation method. So this is a bit more advanced and optional for what we're doing this week. But in case you needed it at some point, this is how you do it. So just remember, when you do the aggregation, if you don't say anything, if you don't provide this ag function, you will get the first output. If you want average, sum, maximum, minimum, anything else, then you have to explicitly say what you want as your aggregation function. Yeah, so does this make sense, or is it overly confusing? Yeah, okay, good. Yeah, so that was aggregation. Let's do something simple before we do another bit more challenging thing, and that's simplifying a geometry. So this is something that you might need. Very often it's a bit more like cartography related. If you want to make a map and you have a lot of like details, then you might want to get rid of some details if they're unnecessary for your audience. For instance, if you're making a map of metro lines in Helsinki, the real map of the metro line may not be so straight. But if you want to just tell people how to go from A to B, do you need to put all the curves and all the details of the route? Probably not. So this is an example of a case where you may want to simplify something. Or if you are making a very simple topography map of Finland just for showing like how Finland looks like on a map, and the map is not going to be used for hiking or orientation or anything, then do you need to have all the rivers with all the details and curvatures? Probably not. It may not even look good if you have so much detail on your map. So it's a bit like cartography related. But if for whatever reason you need to simplify a geometry, there is a way to do that. So Shapely has a function that allows us to simply simplify our geometry. So again, this is provided by Shapely because it's a geometry operation, but through GeoPandas we can just do it directly. So the example we have here is the Amazon River in South America. So it's a very long river. And of course, it has a very complex shape if you want to have all the details or a lot of details. But if you want to simplify it into a more simple looking polyline, this is how we do it. So this is what we are trying to do in this part of our lesson. So as usual, let's run the first cell to define the path to our data directory. The next thing I'm doing, the code is already typed in, is loading our data. So I'm importing GeoPandas and I'm reading the data. So my Amazon River is saved as a geo package in my data directory. So let's run this and take a look at our data. Yeah, so it's you just have one row in your data. It's just one river. It is the geometry is a multi-string, so you have a multi-line with a complex shape. And you have some other attributes that we are not going to use now, like place name and so on. So let's check the coordinate system of this. And this is an important part of the process, and I will tell you shortly why. So this is the coordinate system of our data. It is Mercator 2SP, so it's not very familiar for us, probably because we haven't worked so much with data from that part of the world. Some of you might have some experience, but anyway, it's a coordinate system that is not very familiar for us. It's from that part of the world. But yeah, one thing that is important for us here is the unit of the coordinate system. So we can see it's a metric system. So the units are in meters. So that is what is important to us, because when you are doing the simplification, we provide a parameter that you will see shortly, and that tells in that unit, like kilometers or meters, how much you want to simplify your geometry. So that's why it's important to know what is your coordinate system and what is the unit. Is it degrees? Is it meters? Is it kilometers? So let's just quickly visualize our river to see what it looks like. So this is how the Amazon River looks like. So the shape is rather detailed here. You have a lot of curves. And what we want to do is to simplify or generalize the geometry a little bit. So this is how you do it. So from Amazon, which is my geodata frame. So so there is a function called simplify that we will use. What this function does is it creates a new geometry column. So you remember in geodata frame we have a geometry column. When you simplify, it just creates a new geometry column. So it doesn't automatically create you a new data set or new. Yeah, so you will see how it works soon. So then you can choose what you want to name it. So I want to just name it simple geometry. So let's just name it simple geom for short. So in my output data, there will be a new column storing the simplified geometries. And then this is how I create that. So from my Amazon, which is the name of my geodata frame, I will access the function or the method simplify. And what you need to provide here you have to specify to what degree you want to simplify. So you have to provide a parameter called tolerance. And for that, you have to provide a value. So this is 20,000 meters. So it's the same unit as your coordinate system. That's why I checked. So I want to simplify using a tolerance of 20 kilometers. So what it does, it just looks at, there is some algorithm behind this and how this is done. So what it does is just, it looks at, so you have many points along your line. It's a multi-line, it's a multi-string. So it just gets rid of the lines which are too close to each other, which results in all those details. So the threshold is 20 kilometers. So if there are points that are less than 20 kilometers away from each other, it just removes them. So that's the threshold we are using. And the threshold we are providing is a parameter called tolerance. And remember, it's in the same unit as your coordinate system. So if you provide a bigger number, the line becomes even more simple. So you can go with 40 kilometers, 60 kilometers, whatever. So depending on your need and how much you want to simplify, you provide a value here. So that's one thing. So if you just now I won't do it here, but you try it on your computer. Just plot this. So now that you did run this code, and just plot this. Amazon.plot and see what the output looks like. Did anyone do it already? Does it look any different than the original? No, it's the same. And the reason is that if you now try Amazon.head and see if you have a new column there that you didn't have in the original data. Yeah. So we have a new column called simple geometry. So automatically, it's not recognized as the new geometry. So if you want to use that for your visualization, you have to set it as your geometry. And we have done this before. So I will just create a new data frame, just overwriting my original Amazon. And what I do, I just set the geometry. So I will tell GeoPandas that use a different column as my main geometry. And then what you need to do is provide the name of that column that you just created. So it was called simple geom. And then I will just plot it again. So now you can see that it looks simpler than the original. So yeah, so simplifying geometries is as simple as this. Just remember what it does. It adds a new column, a new geometry column that will not be automatically recognized by GeoPandas. You just have to set it as your geometry. So it doesn't change the data much. You can, again, change back to the original geometry if you don't want to use the simplification. Yeah, okay. So I guess this is simple. Are there any questions? Okay, now that this was simple, let's move on to something that is a bit, it's not complicated, it's just a bit different. So, and that's reclassifying data. Well, I'm sure you have made many maps for many different purposes, and very often you end up using some kind of classification, and there can be a number of reasons why you reclassify your data. Sometimes you reclassify your data because, depending on what you need your map for or your data for, you need it in certain classes. So, for example, you have gotten the certain classification from some official, like for example in Statistics Finland, population always comes, like age groups come in a certain groups, certain classes. So you want to comply with that classification, so you may want to reclassify into that system. Very often when making maps, we reclassify because we have so much detailed values. So if you want to make a map of regions by population, probably there are not many regions that have exact same population. So what you end up having if you don't classify is a map that just looks like a mess. Because probably there are not many cities in Finland that have exact number of population. Even if it's different by 5 individuals, it's different. But the map looks like a mess. So very often you use classification. Instead of having like population by exact value, you have ranges. So you say if population is between 0 and 1,000, this is the color. If you're visualizing it, 1,000 to 2,000, this is the color. So there are many reasons why you often use reclassification in your data. So we will see, and there are some classifications that we are very comfortable with, we use very often. For those of you who use ArcGIS, probably you have used natural breaks quite a lot because that's like the default, unless you change it in ArcGIS, and I guess in QGIS it's also built in. So that's one thing we use a lot, but there are a number of algorithms you can use for your reclassification, or if you don't want to use some algorithm and automate the process, you can just use your own classification. So you might decide to classify based on certain thresholds, so that you can do as well. So this is what we are going to do now in this last part of today's lesson, do reclassification. So first we will go with those algorithms, so built-in automatic classification, see how that works. And then we will do a custom one. So we will make our own classification based on certain conditions. So this is another scenario in which you might need to do some classification. So again, we will work partly with the travel time matrix. So we have information about travel times. Imagine you have access to this data, and since you are good at GIS, you want to use your skills, and you want to find a home for yourself to rent or buy. And since you are good at GIS, you just want to use your skills to shortlist some of the areas that might be potentially interesting for you. And you have 2 criteria here. Your workplace is near Central Railway Station, so you want to get there within 30 minutes, so you don't want it to take longer. So that means that you have to live in Central Helsinki to be able to get there in 30 minutes or in a short amount of time. But then again, living in center of Helsinki means that probably the rent is quite high. Central areas are expensive. So you have a second criteria, and that's based on your budget. That, okay, I cannot pay more than 1,000 euro rent per month. So based on this, you want to make a selection of what are the areas where I can reach Central Railway Station within 30 minutes, but at the same time, the rent is not more than a certain amount. In this case, we don't have data about the rent, the amount of rent, but we use another data as a proxy of the price, and that's the center from the distance from center. So let's just assume, in real life it's not as simple, but let's just assume that the farther you are from center, the cheaper the home is. Well, generally speaking, it's a bit like that, but of course from neighborhood to neighborhood it can be different. But since we don't have rent data, let's just do that. So we have 2 conditions. We want it to be further than a certain distance, so it's not super expensive, but at the same time, it's within 30 minutes from railway station. So this is something that we will do in the latter part of this part of our lesson. Yeah, so the good news for us is that, again, there is a library already that makes classification very simple for us, and that's a library called MapClassify that we will be working with today and later when we work with raster. It is a part of a bigger library called PySal, that I talked about briefly in the first lecture. So it's a big spatial analysis library that we are not covering here. But if you want to do more spatial analysis, PySal is a very good library. And that map classify is part of that. Some map classify functionalities are already built in matplotlib and GeoPandas. So if you want to, we will see it soon. If you want to just make a quick visualization and classify at the same time, you don't need to specifically use map classify. It's built in matplotlib. So yeah, so that's the library that we will be using for our classification work. Yeah, so let's get it started. So the data we will be working with is, again, this travel time matrix. So let's run the first cell to define the path to my data, to our data directory. Then I'm loading my data, the travel time matrix, same file, travel time to Central Railway Station. So let's just run that and take a look at the data. So we have seen the data before. We have these columns. Yeah, so this is the same data we worked with, so we don't have to go through it again. But yeah, so as I said, there are a lot of algorithms developed by scientists, mathematicians, whoever, that work quite nicely depending on what is your goal, what is your preference. So there are a number of classifications. So very often you might just use an equal interval. So you have values ranging from 0 to 100. You just go with the equal interval. So every 25, 0, 25, 50, 75, 100. That's one way of classifying, and it works well depending on what you're visualizing or what you need the classification for. There are other algorithms that are very common in GIS. Natural breaks is fairly common. They have a lot of mathematics behind them. So natural breaks is an optimization algorithm. So what it does, it looks at the variance. It creates some classes, and it just optimizes the classes to minimize the variance within the classes and maximize the variance between classes. And then somewhere in between, it puts the threshold. So this is some optimization method. There are also other ones, like you can go with quantiles, or different percentiles. So there are different ways, and these are built-in map classifiers. So if you want to use any of these for your classification, you don't need to do any math. You can just use this library to do it kind of automatically. So let's get it started. And so one thing that you should also pay attention to when you're doing the exercises, because you will be working with the similar data. In this travel matrix, the missing values are marked as -1. So if you're visualizing, if you're when you're doing the classification, if you have the -1, it will just mess with your classification. So first deal with that. In this case, we are removing all of them by just doing this condition. So I'm rewriting like this. I'm recreating this accessibility grid variable, geodata frame, by excluding any row in which I have PTR/TT, which is the travel time during rush hours by public transport. So PT is public transport, R, I guess, is rush hour. That is, I will keep everything that is over 0, because I know that the non-value is -1 in this data. So if we just run this, we get rid of all the missing values which were marked as -1 in this data set. Again, when you work with the data, it's important to check the metadata, so you have this information. So next I want to just plot my map and use a natural breaks classification for my visualization. So I will plot this accessibility grid. I will just copy the name so I don't have to type it. And then .plot. So this much is easy. We have done it before. But if you want to add more details, well, one thing we already saw, you can add the name of the column that you want to visualize. So I want to use the column PTRTT. So the public transport. So this is the column I want to use for my visualization. So when you're using matplotlib, in this case, if you're making a quick plot and you want to use classification, you don't need to classify separately. So one nice thing in GeoPandas is that you can just do it on the go. So the only thing you need to do is to provide a parameter called a scheme. So this scheme is basically a classification method. So, and you can use any name from this list. So you can check the documentation to see how they should be exactly spelled. But with natural breaks, I know that it is written like this. So it's natural with N capital _ breaks with B capital. So if you just provide the name of the classification method that is built in that library, it should work fine. So with natural breaks, another thing you need to provide is the number of classes you want. And you can use any value. I've tried this before, and 9 seems like a reasonable. You know, with many things, and for example, in classification, you need to do a bit of trial and error. Like with this number of classes, there is no magic number. You just need to see what works well for your data. Another thing that we can provide here to modify the colors, and this we will cover next week, but yeah. So another thing is color map. So what range of colors do you want to use? Again, if you check the documentation of matplotlib, there are a number of built-in colors. So I'm going to go with a color that ranges from red through yellow all the way to blue. So it's a very common color scheme that we use a lot in GIS, in making maps or any kind of visualization. So this I know from the documentation. So there are a lot of like these color schemes you can check and use. So this is just one, red, yellow, blue. And then we can provide a line width for our map, for our geodata frame. And then if you want to add a legend, which is a good idea because now you're using classification, you just set legend to true. So now you can see it's taking a bit longer than usual. Usually when we put .plot, it's just in the same moment you get the output. Now it's taking a bit longer because it's doing classification for you. Yeah, so we took like 10 seconds, you get the output. So this is the grid, and you have classified it into, well, you use natural breaks and it made this classification for you. So 0 to 30, 30 to 43, 43, 54, and so on. So if you are doing just a map, you need the classification only for your visualization. You don't need to do it outside, like separately. When you are doing the plot, just provide a parameter for scheme, and that's the scheme you use for classification. So yeah, so let's make a couple of maps. Let's try this with walking distance. So I will again make another map based on this accessibility grid. This time I use a different column, and the column I'm going to use is the walking distance, which is named walk_d. As the scheme, I will again use natural breaks. Later we will try something else. Again, I will go with k equal 9 as the number of classes I want in my output. For your color map, you can choose what you like. I will go with the same one. Red, yellow, blue. You can also copy what we had earlier so you don't have to type everything. So again, it takes a bit of time because it does the classification. So the visualization here, the first one we made, it's a bit more complex because public transport, it was based on public transport travel time, and that's different in different part of cities, a different part of the city. So some places might have better connection. For example, if they're on the they have a metro station or a train station, some places may not be so accessible. But when we do the same map based on the walking distance, then you get this radial pattern, which makes sense because it's purely based on the walking distance. So the farther you are, the farther is the walking distance. So yeah, so we could get this nice radial pattern using natural breaks. So this was for visualization. So if you just want to visualize, just do it while you're visualizing. But if you want to classify and add the column, for example, to your data, if you want to use the reclassified values for your analysis, then we have to do a bit more work. So let's import the library map classify that will help us do the classification. Then from that library map classify, then you can access natural breaks. So again, I'm using natural breaks. But note that this time it's written this way. So it's a function this time, and it's called natural breaks, and it's written this way. Then you have to provide the name of the column that you want to apply the classification on. So the name of the parameter for that is y. So for y, you provide a geoseries, a column of your data. So from my accessibility grid, I want to apply the classification on this column this time. So PT, R, TT. Then again, it's natural breaks, so you need to provide the number of classes you want to go with. And then if you run this, it gives you this output. So it does the classification like this. Now it did not modify your data. So if you look at your data, nothing has happened. You just did perform the classification for you. And it's telling you that, okay, these are the bins of the classification. This number of values fell into each of these bins. We will see later how you can add this to your data. But you might have slightly different values compared to me because there is a bit of randomness. So it's an optimization algorithm. So every time there might be a bit, like probably it looks very similar, but something might be slightly different. And that's because there is a bit of randomness in the optimization algorithm. So let's try this with a different classification method. So I'm just going to copy this line of code that we had, and I will just edit it slightly. So instead of natural breaks this time, I'm going to go with quantiles. So I will just replace natural breaks with quantiles with Q as capital. And then when we go with quantiles, of course, you don't need the number of classes anymore because it's quantile. So let's just run that, and you get these classes. So if you want to access the threshold values, so you can see the threshold values like this. If you want to access them like programmatically, if you want to do something with it, some calculation based on it, then you can access them easily. So I will create a classifier object that we will work with later on. So classifier and for that I will just copy what I had here. So I will do these natural breaks with 9 classes using the PTRTT column. So I don't have to type it again, but this time I'm storing it into this variable called classifier. I had a typo here. So then you can access the bins, those values that are used for classification, those thresholds, using classifier dot bins. So this returns you an array that has those values that are used. So these are the thresholds based on which the classification was done. Okay, so what if you want to, so now we want to apply it to our data. So now we just saw how you can apply the classification during the visualization, also how you can access the bins and so on. So let's apply one of the PyCell classifiers, one of those built-in ones, on our data and classify travel times by public transport into 9 classes. So if you want to apply it to your data and then, for example, store it as a column in your data, then you have to initialize the classification. And this is how we do it. So let's create the object again, classifier. Then from map classify, which is the name of the library we are using for this, I use natural breaks, or it can be anything else from that list. And this is how you initiate that classification. And then, for example, we will see you can use this to apply it to your data. Then, so .make initializes a classification object for you, which you can use later. Because it's natural breaks, you need to also provide a k value, number of classes you want. Now that this is, so let's run this. Now that this is initialized, so it can be a bit like, it can be like a function. You can apply it. So we have seen already with pandas that you can apply a function to your panda data frame. So now you can use the same thing here. So I will create a new variable called classifications. Then in accessibility grid, then you provide the name of the column that you want to apply the classification on. And it can be, it's a list, so you can apply the classification at the same time on multiple columns. So I will go with the public transport travel time, which was called PTRTT. And this is a pandas thing that we have used before. So you can just apply a function. In this case, we just apply the classifier object that we just created. So you create the classification here. It becomes an object stored under a certain name. In this case, we name the classifier. Then in pandas, you can just apply it to your data. And then let's just look at our data to see what we have. Okay, I have a typo. It was classifications. So now you can see that it has classified your data, so you know each of them has fallen into a class. So these are the class values. But what we haven't done yet, we haven't added it to our data frame. So it's just a new data frame with showing you that each index has fallen into a certain category. So of course, adding it as a new column is probably what you want in your analysis, but before we do that, let's check the output of this. So let's check the type of the classification. So you can see it's a data frame. We don't have any geometry or anything, so it's a simple data frame. So if you want to create a new column, which is probably what you want, is easy. So you just provide a name for it. So in my accessibility grid geodata frame, I create a new column called NB PTRTT. NB is short for natural breaks. You can name it anything you want. So there will be a new column with this name created, and then the rest is what we just did. Accessibility grid, then you apply your classifier. And then we have the dot head to see what it looks like. Yeah, so you can see the original values, and then you have the new classes that you created for your values. So a few things to remember. If you want to classify for your map, you don't need to do any of these things. Just use a scheme, say what classification you want. If you want the classification to be added to your data, then you have to initiate a classification using map classify library, using any classification algorithm you want, and then you can add it as a column. Then you can do whatever you want with that column. You can visualize it, you can just use it for any other calculation. So that's up to you what you want to do with that. So now we have our values there. So if you want to visualize it, you can just do it easily. So let's quickly visualize this using this new column. So accessibility underscore grid. Then I will just plot it. And for plotting, I will use this new column that I just created. So it was called natural breaks MB underscore PT underscore R underscore TT. Then you can specify what line width you want for your visualization. And then let's also add the legend to our map. So this does the same thing. So if our goal was to just visualize the map, these whole steps were not necessary. But the output is the same as doing it like scheme equal natural break. But of course here it's already classified, so you don't need to provide, you shouldn't provide a scheme anymore, because then you will reclassify your reclassified data again. One thing is, yeah. No, not automatically. You have to do it manually, and it's a bit of work. We can get back to that next week, but it's a bit of work with, yeah. Yeah, here it just automatically does it based on this column. Yeah, so one question we often have, like we ask ourselves, when you want to do classification is like, okay, how do I classify my data? Of course, one easy option is to just go with whatever we are comfortable with, natural breaks, quantiles, anything. But what you're normally recommended to do is to explore your data. So look at the values, see how's the distribution, and then based on that, you might come up with some idea what algorithm, what classification method might suit you better. So one way of exploring your data that is good for classification is by looking at the histograms of your data. So you can easily create an histogram of your data to have an idea of how's the distribution like this. So accessibility underscore grid. And then provide the name of the column which you want to use for creating the histogram, and then dot plot. So we are using matplotlib again. This is powered by matplotlib, and then hist. So what you need to provide as an input is the number of bins you want to have in your histogram. So it will be divided to how many bins. So I will go with 50. You can try different numbers if you want. So this gives you a histogram. So it gives you some idea how is the distribution of your values. So for example, around 50, you have a peak. So you have a lot of values that are around 50. So you might get some idea how you want to do the classification. For example, for this kind of distribution, probably equal intervals may not be the best, because then you end up with so many values in here, not so much toward the end. So here there will be almost nothing. So probably that's not the best way. But yeah, so by exploring your data, you can get some idea how you can classify. Let's run this. So this is the same thing. So we are creating the histogram again, but this time we are accessing the bins of the natural breaks. And we are adding it to our visualization. So you can look at the code later in detail, but this is what we did. So it's the same histogram. At the same time, I created a natural breaks classification here. I created this object, and then I read the bins of the classification. So I read those thresholds of the natural breaks, and I just added them as a vertical line, which is dashed with line width of 1 to my map. And I applied color black. So this K is black because blue is B. They have used K as black. So yeah, so this gives you some idea. So if you apply natural breaks on this data, this is how it is classified. So it's distributed like this. Let's try the same thing for quantiles. So I will just run this. Let's see how it works. So for quantiles, it looks like this. So it tries to put same amount of observations or points in each of your classes. So you end up with this kind of classification. So trying this kind of things helps you find out which classification might be better for your work. In your own time, if you want to practice this a bit more, you can try the same things with a different column, car RT, for example, or any other column that you might find more interesting. So one thing that we will not go through, okay, let's go through this one. We still have a few minutes. So applying a custom classifier. So getting back to the question we had at the beginning. So we want to find places that are within a certain amount of time away. So I want to keep places which are less than 20 minutes away. And walking distance is 4,000 meters or more. And the reason was that I wanted them to be a bit cheaper. So I'm assuming if it is 4 kilometers or more away from center, then it is probably cheaper. So we are going to classify based on this. So let's just run this. So it returns false. So I'm just trying this for the first row of my data. Just see. So the first row, the first grid, it is false. So if you want to, for whatever reason, if you don't want, so what this returns is true or false. So it's this Boolean value. If you want to have it as a number, like 0 or 1, like as binary, then you can just easily do that by converting it to the integer. So I just put an int, and inside it I can just paste the same thing, but let's try it for a different column. For a different row. So instead of 0, I will go with 11293. So you can try it out for any other column you might be curious about. And you get 1. So if you had tried it for this one that was false, you would have gone 0. So if you need, for whatever reason, 0 or 1 instead of true or false, then you can just convert it to an integer. So now getting back to this original question we had at the beginning of this lesson, and that was finding suitable areas for looking for an apartment. Remember what was our criteria. We want the place to be within certain distance, travel time in terms of minutes, and also further away, like more than 4 kilometers away from center, so I can afford it. So I want to add a new column to my data with 0 or 1 value, just telling me whether it's a good area to look for an apartment in or not. So let's just run this. What it does here, it creates me a new column called suitable area. And inside the suitable area, I'm using lambda, which you have used before. So instead of this, you can just use apply, define a function based on this condition, and then just apply it here. But we have seen before, you can use lambda to just save a few lines of code. So instead of defining a function separately and then applying it here, using lambda, you can just define and apply the function at the same time. So with lambda on the row, I'm applying the same thing I did earlier. So creating an integer from this condition, so it returns me either 1 or 0. and access is 1. So if access is 1, it applies the function row by row. That's what we want. We want to check the condition for all our data. With access 0, it will apply it across columns. So in our case, we want to go through the rows. So that's what we have. So let's just run that. And then you can quickly look at head to see what we have. Let's just copy this so we don't have to type it. So this is an example of how we can create a custom classification. So we just created a column called suitable area with Boolean values 0 or 1, telling us whether the place is suitable or not. So if you want, of course, you can also get the counts, like how many suitable areas are there for me to look for an apartment. So I can just provide the name of the column that I just created. Sorry, I'm a bit going faster. We're a bit out of time. Suitable area is the name of column I just created. And in pandas, there is a method called value counts. So it just counts how many values you have, how many of different values you have. So it just tells you, in your data, there are only 9 values that returned true for me. So in Helsinki, if you have those 2 criteria for finding an apartment to rent, there are only 9 grid cells, according to the data, where you might have a chance of finding the apartment you want. And then if you want to just visualize it, let's run the next code, and then you will see the 9 cells are somewhere around there. So yeah, so that was an example of a custom classification. In the exercises, we are doing another kind of custom classification that we didn't go through now, but the assistants will help you if you have problems. And of course, I've added a hint here. So using map classify, the same library we work, there is also a way of defining a custom classification, defining the threshold. So there is an example here. I'm sure you will figure it out. And if there are problems, we will help you over Discord and in the help sessions. But yeah, this is another way of applying a custom classification. Yeah, so that's it for today. See you next week.